Good morning, everyone. I'm Halley Darling. I'm here from UL Solutions, and I'd like to talk to you this morning about the impacts of albedo estimation methods on energy estimates. First, of course, I'd like to acknowledge my colleagues on this project, Ren Darwali and Lucy Taffer. Thank you both for your help with this one. So first, I'd like to go over the agenda for this talk, just really quick. I'm going to talk initially about our background and motivation for this project, different albedo measurement and modeling choices, the sample locations that we took for this project, our energy modeling assumptions, the results, conclusions, and some future work. So first up, background and motivation. As we all know, albedo, it's the ratio of reflected solar irradiance over the global irradiance, and this depends heavily on the reflectivity of the surface material. So I'm going to talk a lot on this one about albedo differences, and energy differences. So if you see any numerical values here, that's referring to albedo, but I'm going to verbally say them as percentages. So typical ranges for albedo are about 15 to 20% for darker soil, 20 to 30% for lighter soil, 20 to 25 for vegetation, and up to about 75 to 85% for fresh snow. And of course, albedo has a significant effect on bifacial energy. Here below is the formula for the relationship between the backside irradiance and the albedo and GHI. And of course, big motivation here is, at least in the US, the Inflation Reduction Act of 2022 is going to have major impacts on solar installations over the next 10 years. We see here a graph from Woods Mackenzie and SEIA depicting the specific amounts of estimated solar installations over the next 10 years. And of course, one of the things that we're seeing in the market is that the market share of bifacial panels is increasing. So we asked ourselves a couple questions to start with this project that we try to answer. So how much difference do different sources of annualized albedo produce? Given different albedo estimates, how much does a generic bifacial project vary in energy? Is there a relationship between the differences in albedo and the resulting difference in energy? And do on-site measurements capture typical long-term albedo conditions? So to just talk quickly about some albedo measurement and modeling. Satellite modeled albedo, this is a product that is being offered more and more frequently nowadays. Services that have been offering solar resource for some time are incorporating albedo into their products. Each provider is using their own custom algorithms for albedo modeling, and this often involves imagery of about 1 to 4 kilometers in resolution, as well as historical and modeled snowfall time series data. Satellite modeling offers a long-term solar resource, so we're talking 20 plus years at hourly or sometimes even finer temporal resolutions. However, albedo statistics are generally reported as monthly, so that might be a typical or average year albedo or specific years. So for this project, we did a couple of tests here, and our sort of parameters here, we tested a sort of default scenario of just a flat 20%, which we're calling like PVSys albedo default, since that's what pops up most of the time. And as well as 3 monthly average albedo sources, which you're calling here models A, B, and C, and then an average of all of those monthly sources on a monthly level. Additionally, we'll look at some interannual variability statistics from 2 time series-based albedo datasets, which we're calling models 1 and 2 here. So the other half of albedo estimation is on-site data from solar meteorological stations, or SMS. These are used to obtain a point location solar resource, often at future development sites. These stations are deployed for about 1 to 2 years, and if I can direct you to our Measure, Correlate, Predict poster over here in red for a deployment length uncertainty impacts. I'd love to have more people take a look at it. So solar resource often uses a combination of the long-term satellite modeling and on-site measurements to derive long-term adjusted solar resource values. by a variety of approaches, but measure, correlate, predict is a pretty common one. These stations often include several pyranometers, including a downward-facing pyranometer to calculate albedo. So next I'd like to talk about the sample locations for this project. And I have to mention our field services. So we've collected albedometer data at over 150 locations, and that gives us a strong understanding of both irradiance and albedo in the United States. From this data, it's possible to understand some regional differences in albedo. And all of these sites have extensive manual validation and QA/QC to remove erroneous values. So these are the states that these 34 sample sites that we are using for this study are in. It's about 15 states across the U.S. Doesn't quite cover all of the regions of the U.S., but it covers a fair few, so I think that produces some interesting results. Next, I'd like to talk about the energy modeling assumptions we did for this project. So we did this project in PVSYST. We set up a generic single inverter block with generic pan and OND files from the PVSYST library. Specifically, our panel is a 440-watt mono-PERC panel with 80% bifaciality. That's maybe a little bit of an aggressive bifaciality, but the market seems to be trending towards higher bifaciality. As well, we applied a Fresnel ARC for the IAM profile. We estimated our trackers to be about 1.6 meters height above ground, and I forgot to put in here, 33% ground cover ratio. As well, we did unlimited trackers for the bifacial simulation and the shading simulation. And so that was true for all iterations of this testing. So site-specifically, we have site-specific site and MET files. The MET data is from solar resource MCP analysis. Since we took the irradiance data at these sites, we had long-term irradiance values. As well, we had site-specific soiling losses from both dust and snow. And what's notable here is that that does include a bifacial benefit for snow reflection and a bit of a penalty for backside soiling. Next, I'd like to talk about our modeling assumptions. So since we're doing a whole bunch of tests here, we kind of try to keep it a little simpler. So we kept the project level albedo as the default 20%. So that would translate to no real albedo benefit to the front side for these simulations. So all we're getting is the backside differences. Additionally, we assumed losses from complex terrain or specific tracker shading to not be included. Those are very project specific and depend on the site and the trees and other obstructions. We also excluded the horizon profile from PVSYST as our observations on site would kind of inherently include some horizon impacts since we're not able to back those out. So no horizon profile. We also assumed some standard assumptions for electrical and transformer losses. And no post-processing losses applied. So we didn't do any point of interconnect, wind stow, sub-hourly clipping, or availability losses. And we are only looking at energy evaluated on a first-year basis, so no material degradation. So here are two histograms of the sites that we looked at. We have, again, our 34 sites, and we have albedo on the left and energy on the right. And so the numbers are a little small, but the gist of it is that the majority of our data points fell within the 18% to 24% albedo range. And again, this is annualized albedo, so you might have higher months, especially in snowier sites. But we did have a couple sites that were higher albedo as well. So when we ran energy, we had, interestingly, a similar distribution for the energy values. So this is coming in at about like 3.8 megawatts to about 5.5 megawatts. So this is, again, a single inverter block, so not very large. But obviously the energy relies probably more on the irradiance than the albedo here, but it was interesting to see. Next, I'd like to talk about some of the results from this study. So here we have some box and whisker plots of the albedo, again, on the left and the energy on the right. So again, our default like 20% across the board scenario is kind of like a baseline here of if we didn't try to model albedo at all, and we just kind of applied it flat. And it's doing pretty well, and I think that is due to the fact that a lot of these sites are within a very typical albedo range. So keep that in mind when we're looking at the rest of this data. Model A seems to be performing quite well in both albedo estimate and energy estimate. Models B and C, Model B seems to be a little low, and Model C is a little all over the place. But the average, interestingly, kind of compacts down that range to be a little bit more precise. And even if it's not quite at the 0% difference, it's doing pretty good. And what's also notable is on the energy side, we are looking at the bulk of these estimates being within 1% of the difference in energy from the on-site scenario. And this is more or less the same data, but in a tabular form. And you can see here especially that the average scenario is producing a reduction in the standard deviation. So you can see, especially on the energy side, its mean is 0.3% under the on-site scenario, and the standard deviation is about 0.3%. So I found that interesting. Next, I have some scatter plots of the difference in albedo versus the difference in energy. Again, albedo in numerical values and the energy in percentages here. I've also color-coded these by the on-site albedo, so you can especially see in the default 20% scenario, very linear in both the relationship and in the distribution of the albedo, and that makes sense if you're, subtracting like a specific value across the board. It's going to kind of look like that. But you can see in the other sites we also have a very linear relationship, but in different capacities. So Model A, as shown in the previous plots, more concentrated around the center. Model B a little low, and Model C maybe a little high even. So the other thing that's noteworthy for this slide is that the slope of all of these regressions comes in at around 6. So that's telling me that a 6% difference in albedo, so going from like 20% to 26%, is producing about 1% energy difference. For this scenario, it might be different for different setups. Next, I'd like to talk about interannual variability of albedo. This is just points on states. Obviously, for these model providers, they would maybe have more specific interannual variability statistics, but just as a baseline here to kind of show what regions are producing high interannual variability and which ones are producing lower interannual variability. So we can see here, especially in the southern portion of the United States, not a lot of IAV. And that's expected. Most of the IAV is derived from snow differences. But you can see in the Northeast, there is a significant amount of IAV where you are getting different amounts of snow, different time periods for snow. So when you're getting your albedo and by how much can change quite a bit. So this is Model 1s. And this is Model 2s. Model 2 generally predicts higher IAV kind of across the board here, but you can especially see that like the Midwest to the Northeast is quite high. And I'll clarify that the high values here are about 4% albedo difference in annual albedo difference. So again, that's about like if you go from a 20% one year to a 24% albedo the next year. So one of the things we were able to look at was the IAV of just 2 years of data from our on-site measurements. So we have a sample here of 5 sites that had 2 years of albedo data. And what's notable here, first, is that this is a very small sample size, so grain of salt, both in number of sites and years of operation. So this is just more to depict how much variability you can have when you're taking 2 years of data. And you can see that regions with low IAV in general are also producing low IAV here as well. So for instance, California here produced about 0% difference in year to year. The Texas one produced only a little bit, like 1%. But also the maximum monthly values are interesting too. So the monthly differences in albedo from year 1 to year 2. California, the largest one was 2% difference, and in Texas, the largest one was 7% difference. But if you look at the more northern states, Pennsylvania and Ohio here, you see a fairly significant amount of IAV and maximum monthly difference. So about 2% for these sites for the IAV difference, and 13% for the maximum monthly difference. So if you're modeling your albedo on like a monthly basis, that can be a significant difference. Some conclusions. So the annual albedo differences differ from on-site measurements by an average of negative 1.7% with a standard deviation of 2.3% across the 3 models. But that amount of difference only translates to about minus 0.3% plus or minus 0.5% in energy differences. Averaging these 3 models monthly before analysis maintains the same average difference, so the 1.7 and the 0.3, but it further reduces the standard deviation to 1.5% for the albedo and 0.3% for energy. The regressions of the albedo difference to energy impact suggest a 1/6 factor for this experiment. So again, 6% annual albedo difference translating to 1% energy difference. On-site albedo measurements of only 1 year may not capture interannual variability at very varied sites. So 2 models of time series data can predict that the IAV can be as high as about 4% albedo difference year to year. And 2 years of albedo data at highly varied sites, such as snowy regions, can provide additional coverage for this effect. In these high IAV environments, the on-site albedo measured at the maximum or minimum could result in about 1% energy difference from a typical albedo year. And to revisit our motivation from the beginning, how much difference do different sources of annualized albedo produce? This should be a negative, but a negative 1.7% albedo difference, plus or minus 2.3%. And given the different albedo estimates, how much does the generic bifacial project vary in energy? Negative 0.3% plus or minus 0.5. Also needs a percent on there. And is there a relationship between the differences in albedo and the resulting difference in energy? And potentially, for this system, it was about a 1/6 relationship. And do on-site measurements capture typical long-term albedo conditions? And this is very dependent on the interannual variability of the region, as well as the length of on-site measurement campaign. Future work. We have 2 potential future work paths here. One is albedo MCP. Measure, correlate, predict analyses have been very strong for solar resource long-term results. So high-quality modeled albedo data sets might be used in conjunction with on-site measurements to produce these statistical regressions on a monthly basis and to better capture the effects of IAV and measurement time periods. So with a measure, correlate, predict analysis, you might not need as much on-site data if you can correlate it to a time series. And as I mentioned, this would probably be most effective in regions with high IAV, but it would be good to verify the low effects of low IAV in regions that have that. Additionally, we could look at some sub-monthly modeling. Right now, a lot of the modeling is on a monthly basis, but our on-site data has a finer temporal resolution. We can have, down to minutely, though I don't think that would be very helpful. Daily albedo or something could be very interesting to look at. So this would be something where we would maybe need some custom software in this regard. So something like PVLib might be a good application. But from yesterday, it sounds like a lot of folks are looking at some different temporal resolutions in their analyses. I don't think this would be much of an effect on our current energy modeling, but better understanding the effects of a sub-monthly modeling for albedo would maybe help us categorize that a little bit better. Thank you. If you need to contact us, here we are.